I see a title there, quantum computers, so it's just a section of...
that's not the title. Okay, so let's go back to... Here's the title.
Okay, so we're still in the geometry of quantum contextuality, talk by Frederick Holbeck, second finishing today. Go ahead, 55 minutes.
Yes, okay, thank you, Christomalis. Okay, so let me jump to where we stopped yesterday. So yesterday we covered a couple of questions, defining what the Cohen-Specker theorem is, what is the geometry of configuration of observable that can be serve as a proof of contextuality, and then I introduced at the end the notion of a degree of a configuration to measure how much contextual a configuration was. And today, my goal is to show you how we can transform this into experiment that we can run on a quantum computer. And no worries, I will get back to the grid again when time's need, so I don't expect you to remember exactly what we said yesterday. If needed, I will re-explain and redraw the Mermin square on the board, of course. But first, let's discuss a little bit about what a quantum computer is, so we are on the same base and we share the same vocabulary for what I need to explain. So first, what's a quantum computation? For this talk, I will consider a quantum computation as something that takes n-qubit states, perform some unitary transformation, you get a new quantum state here, and for the outcomes you would like to measure some observable. Okay? And in practice, the people dealing with quantum computing, and especially trying to use quantum computers, they like this quantum circuit formalism, where your computation can be represented by a collection of sample quantum gates that perform elementary operation. So each wire represents 1 qubit. This is a 3-qubit computation, and on my first qubit I will perform an Hadamard gate, which is a gate which is responsible for superposition. Then I perform an X gate, which is the same as the polymetrices we met yesterday. And here on the second qubit I do another transformation, and here I have a gate which acts on 2 qubits at the same time. So if you are not familiar, I will explain later what this gate is. But then at the end of this collection of elementary gates, we have a new... sorry, it's not good. Is it better? Okay. Oh yeah, now I can hear me. Okay. So at the end of this collection of elementary gates, we have a new quantum state, and we perform a measurement in some basis, which correspond to the observable here. So again, if you're not familiar with quantum computing in this formalism, but I hope some of you have already met this, you can think of this gate as the quantum analog of the logical gate in classical computation. So an interesting question is that sometimes people ask when you look at conference about quantum computing is, do we have quantum computer? Does quantum computer exist? But so you can actually ask the same question in the 50s. When do you decide that we have a classical computer? I mean, at which level of achievement you can decide that this is a classical computer? Because in the 50s, the first machines were very limited. So there are universities but mostly industrial companies who try to build a quantum computer, and there are some quantum computers available that you can access through internet, and they are noisy and very limited in scale, but there are, at least that's what the manufacturer claims, they work on the base of quantum computing. And even if they are not performing as we would like them to perform, they do exist, and you can play with it. An interesting thing that we should also keep in mind is that today there is no theoretical obstruction to the fact that there will be someday a quantum computer of large scale. It's, of course, a very, very difficult problem, very highly engineering stuff, and we don't know when it will be, but it will be very surprising to prove that it's not possible to build it. Okay? And lately, there have been a lot of progress in the quantum hardware size. Okay, so quantum computers exist. They are very noisy. And with your email address, you can have 10 minutes of time of calculation on the IBM cloud for free every month. And if you are a researcher and you write a proposal, they may give you more time of computation. And how does it work, basically? How do you use a quantum computer? Well, here I don't know if you can read, but basically I have so there is a language. Here this language is called MPQP. It's developed by a company in France. What does it say? It says circuit equal quantum circuit of size 3, add Hadamard gate on 0, add a CNOT gate between 0 and 1, add a CNOT gate between 0 and 2. So basically it's describing this circuit. And add basis measurement here. And then run the circuit on different backend Google device, local simulator, the IBM simulator, etc. Okay, and so this basically circuits here create a GAZ state. If you're familiar with 3-qubit entanglement, so it creates these states, and you measure it in the standard basis, and you get some statistics. So here it says that, for instance, we run this experiment. So here for this model, it was run on simulator, but you have the choice of running on simulator or real machine. And here it says that on the 1,000 sample, we get like 1,024, we get 503,000 and 521,111. Okay. What we can do with the quantum computer, of course, people dream about programming very sophisticated algorithm and prove quantum supremacy or stuff like that. And it's for, well, today's machine does not allow you to do it. However, you can also see a quantum computer as an experimental device. Just think of it as something that can help you create some entangled state and perform some measurement. And a lot of questions we are interested in quantum physics or quantum information is about, entanglement of quantum state, and in what we will be discussing today, performing some measurement to discuss contextuality. So what we can do very easily is to perform some sequential delegated measurement. And I'm going to explain a little bit the math behind this. So remember, among the gates that we made before, there was this Hadamard gate, which corresponds to this unitary matrix. And when you apply it to ket 0, it provides the ket plus state. So it's a gate that change of basis between the Z basis and the Hadamard basis or the X basis. And here's a control NOT gate, which is a gate represented by a 4x4 unitary matrix because it acts on 2 qubits at the same times. And what does this gate do? Well, basically, if your qubit here is ket 0, which corresponds to this 2 transformation, it acts like identity, so it does not change anything. But if your qubit on the first wire here is ket 1, which corresponds to the image of these 2 vectors, then it will flip the result of this qubit here. So it's called a control NOT gate, and it just says that if the first qubit is 1, you apply an X gate on the second qubit. Okay? And this gate cannot be decomposed in 2 separate unitary gates. It is a 2-qubit gate, and it's the gate that usually is used to create entanglement. Okay, this is very familiar for all of you? Oh, okay, good, okay. Okay. Well, this very small circuit that I will use a little bit later is a way of delegating the measurement of this quantum state here to an ancillary qubit. So what do we do? I would like to measure this qubit in the X basis, but I don't want to destroy this qubit. I want to keep it for other measurement later. So what we do, we perform a Hadamard transformation. So we change this qubit to the Hadamard basis. We use a CNOT gate to, in some sense, print the result of what we will measure here. And then we do a Hadamard gate to come back to the original state, and we measure this qubit here. So this technique of delegation allows you to make some measurement in different bases without destroying your state and collecting the result on different wire. That will be very important for what I want to do with quantum contextuality. Okay? Good. So now we're going to discuss an inequality due to Adam Cabello, and which he proposed to test quantum contextuality and measure the degree of contextuality of some configuration of context, as we discussed yesterday. So yesterday we described contextuality as a geometrical configuration in the symplectic polar space. And so what we're going to do now is discuss inequality related to this type of configuration, how we can implement this inequality on quantum circuit, and the type of experimental test that my student was doing on the IBM quantum computer. And if time allowed, I'll show you another even more exciting way of testing contextuality. Okay, so remember, so that's the slide to recall what we said yesterday. Contextuality is a fundamental feature of quantum mechanics. If you would like to set up a hidden variable model that reproduces your quantum prediction, this hidden variable model should be contextual, meaning the predefined value should depend on the context. And one elegant proof of this phenomena is this famous, well, actually, I'm sorry, it's not the same I gave you yesterday, it's another one, but it's a Mermin grid configuration of 9 observables in 6 different contexts, and the contexts have different signs. And there is no way you can predefinite value plus or minus 1 value to each node that satisfy all the context. Okay? So that's what we want to test. Okay, so here's the Rio-Negro inequality. So the Rio-Negro inequality, you consider you have a contextual configuration, which is a collection of L context for which there is no non-contextual evident variable model. So which a configuration like the grid, which is proved to be contextual. And we introduce the following quantity. You take the summation of the expectation of your positive context minus the summation of your negative context. Okay? So why is it interesting? Well, if you remember, so the positive context are the context where the product of the observable is plus identity, and the negative context are the context for which the product of the observable is minus identity. So we know what quantum mechanics predict for the measurement of such quantity, because we are measuring identity and minus identity. So we get plus 1, plus 1, plus 1, plus 1. So the boundary that measuring this type of context and building this quantity here, under the assumption of quantum mechanics, it should be the number of contexts itself. Okay, so if we play this game with the Mermin grid, that should be 6. However, yesterday we introduced the notion of degree of contextuality, which is some kind of obstruction for a classical model to satisfy all the constraints of your contextual configuration. And D, if you remember, that was introducing this quantity with this system of equation. It's a minimal number of constraints that cannot be satisfied by your non-contextual hidden variable model. So that's the number of equation you need to flip in order to find hidden variable models that satisfy all the constraints. Well, if you think about it, in the case of a non-contextual hidden variable model, the boundary of this quantity should be the number of contexts minus 2 times the degree of contextuality. Why? Well, the degree of contextuality corresponds to the number of contexts which will be wrong. And being wrong means here that you will flip the sign. So you will have 2 times the number of wrong answers, which will decrease the value of this quantity here. Okay? So and I'm sorry, now here this Mermin inequality does not correspond to the previous one, corresponds to the one that I showed yesterday. It should be plus here anyway. So if you look at the Mermin square, the Rio inequality tells you that if you measure the 6 different contexts involved, so corresponding to the 3 lines and the 3 columns, if you assume that we are in a world which is designed by some non-contextual hidden variable model, well, this quantity will be bounded by 4. But if you suppose that you are in a world governed by quantum mechanics, this quantity will be bounded by 6. And if you know how to do this measurement, then you can check where we live. And yesterday we discussed a couple of geometries. I introduced symplectic polar space of rank 2 and of rank 3 to describe the commutation relation of the 2-qubit and 3-qubit operator. And in the discrete phase space of Andrei this morning, that was corresponding to the ray that you could find. Well, for this geometry, if instead of taking, only the 6 contexts of the Mermin square, you take the 15 lines of this doily, then the classical bound is 9, the quantum bound is 15. And if you go to the 3-qubit polar space, then your number of contexts is 315, and that's the optimal bound you can reach. But the classical bound is 189. So the larger geometry will offer a more robust experience because the gap gets bigger and bigger. Okay. So now the goal is to, question about the Rio Negro inequality. So it was named, so the interesting question is where the name comes from. So it came from when Adam Cabello was visiting Brazil and he named it after, okay. The Rio Negro. All right. Another interesting things I'd like to show you is, so as you see before we do the measurement, so what's important here to create this gap is this context that you cannot satisfy, the context that corresponds to the degree of contextuality. That's what's important in our configuration. And I would like to stop to say a few words about what they are. So the context corresponding to constraints that cannot be satisfied. They play this role because they correspond to this, there are D of them and they correspond to this degree, and in fact they correspond to the gap between the what's predicted by quantum mechanics and by any non-contextually done variable. So for the doily, the 2-qubit operator, well, you can always find a classical model that satisfies everything but 3 contexts. And these 3 contexts that cannot be satisfied will all be 3 disjunct lines.
Is it so-called pilate biplane?
This is the symplectic polar space of rank 2. We call it the doily. It's also called the generalized quadrangle. It's the only 15-3 configuration which is triangle free.
Yes, so I think it's related to this pilate biplane, which is generalization of Fano. Fano is 7 points?
No. It's not the generation of Fano because the generation of Fano will be a projective space of dimension 3, and you will have more lines. You will have the same number of points but 35 lines. Here we discussed this yesterday. But it's related. So this geometry encodes the commutation relation of the 2-qubit poly operators. And if you look closely at where the constraints are located, well, of course, the constraint could be located at different ways. It depends on your hidden variable model you choose. But we know that the constraint will be always 3 contexts that cannot be satisfied. And these 3 contexts that cannot be satisfied will always make 3 independent lines. Okay, 3 independent line is not crazy as a geometry. So maybe we should not be so excited by this. But the next slide will be a little bit more interesting. Remember, we said yesterday that for the 3-qubit polygroup, the number of constraints is 63. Okay. So for the 3-qubit polygroup, the constraint, they form this crazy geometry called the split Cayley hexagon. So if you have a classical model that reproduces as much as possible prediction, the only prediction that you will fail to reproduce, you can arrange them in a way that they will form this crazy geometric configuration in W52. Okay, the set of constraints. And why is it interesting? Because once we understand this, suppose you want to describe the contextuality of another subconfiguration of here. Well, you can study how this subconfiguration will intersect this guy and deduce some property of the constraint that cannot be satisfied in your other configuration. Okay, so we are good for the Rio Negro inequality and the constraint which are this configuration that we cannot satisfy. Okay, so let's move to the test. And how are we going to test the Rio-Negro inequality on a quantum computer? Well, in the circuit model, it's straightforward because we know how to make some delegated measurement. So for instance, this circuit is just a circuit that implements the measurement of the context x, y, y, x, z, z. And you collect the measurement for the first 2-qubit observable here, the second 2-qubit observable here, and the third 2-qubit observable here. So you see here we make a change of basis in the x basis. This corresponds to the change of basis to go to the y basis. So it corresponds to measuring the 2-qubit state in this xy for this xy observable, and we collect the result here. Here we have the y change of basis. Here this is, what is it? Yeah, and there is nothing, no, what's wrong? Huh, something is wrong. No, it's here, okay. Sorry, no. What's wrong in my picture? Let's see. No, it's here. Okay, it's here. This is x change of basis, right? So this is okay. Yeah, because this is the previous y. Sorry. Okay, so this is y. This is x, and now here this is z, measuring z because we are already in the z basis. You just apply a CNOT gate. No, there is no minus sign. It's just, it's a context. So it corresponds to one line in my geometry. No. Yeah. There is no signs. So this represents a context. So a set of 3 commuting observable, and I measure any 2-qubit quantum state here, sequentially following this experimental setup, and I collect the result of each observable. And the result of quantum mechanics tells me that because this context here is, should I get it right? Okay, so this should be plus identity. Then the product here should always be positive. Or the sum mod 2 should be 0. Yeah, please.
Construct such a quantum computational scheme for measuring any context? Or you have to do some job every time?
I mean, you have to well, okay, so the method I propose is that I have an elementary way of measuring my 3-qubit observable. So you need to transform your geometry in terms of a sequence of circuit corresponding to the measurement of every context and collect off the result. Mm-hmm. Okay.
Can you do the same? So this is a real job, or there's a science behind it? So there's a systematic procedure. Do like this, and that.
Well, if you give me, so even if it's a 10-qubit state, but you give me your context in terms of Pauli observable, I can automatically generate the circuit. Yes. Yes. Yeah. Well, because the experiment the first experiment we did with this was for this W52, which contains 315 contexts. So we didn't, implement that by hand. We generated from the geometry and then translated into the circuit. Thank you. Okay, so here's the experiment we got on real quantum computers. So this was done on a year ago on the IBM Kingston. There are some names. And here are the different geometry we tested. The L is the number of contexts, D is the degree of contextuality, so you recover W52, the 3-qubit Pauli asymplectic polar space. On perfect simulator, we find 315, which is what is predicted by the theory. On a noisy simulator, because this computer allows you to simulate noisy simulator, we got this 279, but on real quantum computer, we got 264. And the classical bounds is 189, and that's a standard deviation by which we beat the classical limit. And we did it for the square, which has degree of contextuality 1, 6 contexts, and here's the result. So we beat the classical limit 4. We did for the doily, the 2-qubit polygroup, degree of complexity is 3. We got 13 versus 9. And here, if EP and HP, I didn't introduce them, but they are subgeometry of this space. They correspond to elliptic quadrics inside this space. They are configuration made of 45 point and 27 line. 27 point and 45 lines. The degree of contextuality could be calculated to be 9, correspond to exactly the intersection of this quadrics and this split Cayley hexagon. And again, we beat the classical limit without any problem. Okay. Okay. Well, that's what I wanted to say about the Rio Negro inequality and its implementation. And since I have time, I can also show you another way of testing contextuality. But first, is there some question? Is there any question about all of this?
How natural is this measure of how far you are from contextuality? I mean, you just measure how many signs you have to flip.
Yes.
But this assumes somehow that it costs you a certain amount of work to flip its switch, and you have a cost function like this. But I can have a switch in my laboratory that flips, say, all the signs simultaneously, and then that cost function changes dramatically. So is it just a choice of cost function, or is there something special about it?
I'm not sure I get your point. You're talking about the
degree of
the degree, yes. Okay. So for me, the degree, again, in the Rio Negro inequality, it's half of the gap between what is predicted by classical theory and what is predicted by quantum theory. Okay, and geometrically, if you remember, yesterday I told you that everything boils down to trying to solve the linear system AX equal B. So the degree, in some sense, is some Hamming distance between the image of your linear map A and the value you want to reach, the one that is given by quantum mechanics. Okay, and so you really measure a distance between the two.
My question is, why Hamming distance, not some other distance?
Oh, why Hamming distance? I don't know. Well, it was what was the most natural way to.
Of course, but so do you expect things to change if you adopt some other distance?
Okay, well, I have no idea. We need to look this into detail. Okay. But since we are working over Z2 linear subspaces, Hamming distance was the most natural way, and it was meeting this bound proposed by Cabello 15 years ago. I have just one slide, but a lot of time because I have like 10 minutes more. Yes. Okay, so I have plenty of time to explain this, which is a game, a quantum game, and another interesting way of testing quantum contextuality. So it's called the Mermin Magic Square, and it's what's called a non-local game. So it's a game where two people are playing together against the referee Charlie, and they are allowed, because it's a quantum game, they are allowed to use quantum resources. Okay? So the game goes as follows. Charlie sends one integer between 1 and 3 to Alice, and another integer to Bob, and same between 1 and 3. And both Alice and Bob have to send to Charlie a triplet made of 1 and minus 1. So Alice send back A1, A2, A3, B1, B2, Bob send back B1, B2, B3. When the game starts, they cannot communicate. So they don't know, Alice does not know what is Y, and Bob does not know what is X, and Alice has no idea what Bob is sending back to the referee, and vice versa. And the triplet, they should satisfy different constraints. For Alice, the product of the triplet should be 1. For Bob, the product of the triplet should be minus 1. And both of them win the game if the element of the vector of Alice that correspond to the position of Bob is equal to the element of the vector of Bob that correspond to the position of Alice. So this game is called a quantum pseudo-telepathy game because they have to guess what Bob needs to know what is, because you have plenty of choice of 1 and -1 to satisfy this inequality. It's not difficult. But that the value that Bob will choose for Bx and the value that Alice will choose for Ay is what will allow them to win. So they need to guess what is y and what is x, which they don't know by construction of the game. So there is a classical strategy that allows you to win this game with a probability 8/9. And this classical strategy is represented by this assignment here, right? So suppose, suppose Alice is here, Bob is here. So if Alice gets 1, she will replay 1, 1, 1. If she gets 2, she replay 1, -1, -1. And similarly, Bob, if he gets 1, he play 1, 1, 1, 2, 1, -1, 1. And here, this square satisfies all the constraints, +1, +1, +1. But here we have a problem. We cannot find the value that is satisfies the constraint for both of them. So here, basically, you win this game with this strategy, but not if you pick up this, you got these questions. Okay, so you win the game with probability 8/9. Well, if you allow the player to play with quantum resources, which is basically you allow the player to share entanglement, then they win the game with probability 1. And it's not cheating because having entanglement does not mean you can exchange information. There is no information going between Alice and Bob. There's just some way of correlating the answer, but there is no information. So you don't break the rule that they do not communicate, they just share entanglement. So what happens if they share entanglement? Okay, so this is the circuit, but I need to explain a little bit what this circuit is about. So what Alice and Bob will do is that they will create an entangled state, which is the product of 2 EPR, which will be, so it will be a 4-qubit state, so like this. 0, 1, 0, 1, plus 1, 0, 1, 0, plus 1, 1, 1, 1. Okay, so you can see that it's a product of 2 EPR pair, but between qubit 1 and qubit 3, and qubit 2 and qubit 4. Okay? And so this is the first qubit of Alice, this is the second qubit of Alice. This is the first qubit of Bob, this is the second qubit of Bob. So they create this 4-qubit entangled state, and they start the game with this 4-qubit entangled state. And both of them, they agree on a Mermin grid. So they have a Mermin grid. And one for Alice, and it's the same grid, and one for Bob. So I should, well, actually I can provide you with, okay, so it will be x, y, y, x, z, z. What should I put here? Y, z, zx, okay, zy, xx, and here should be xz, and this should be yy. Okay, so they have this grid together, and this is positive. No, this is negative. So x, y, z. X, Y, Z. Okay, so this is negative, this is negative. Okay, so this is a positive line, this is a negative line. So there is one for Alice, there is the same for Bob. Okay? So they will take 2 of their qubit, and if Alice got so Alice will play with the line, Bob will play with the columns. If Alice get line number 1, she will measure her 2 qubit according to this context. Okay? And she will get the triplet right, because we know that the product of the eigenvalue here should be +1. Okay, so she will satisfy the constraint that the triplet should be +1 for her. And Bob, as he takes the columns, which are negative, the product of his observable will be -1. But what happened on the observable that correspond to, so suppose Alice got 1 and Bob got 2. So Bob has this context, yx, zy, xz. Okay? So here, this is y equal 2, and this is here x equal 1 in Bob context. But when they will be measuring this state following the observable yx tensor yx, they need to get the same result. This state here is in fact a stabilizer state for the subset that you create by multiplying this observable with this observable, this observable with this observable. You multiply each observable with themselves, what you get is a set of observable where everyone commutes. Because remember, these two guys didn't commute. But if you double them, so if you take these two guys, so you have xx, and I do tensor xx to have a 4-qubit observable, and here I had xz, and now I take tensor xz to have a 4-qubit observable. Now these two observable commutes, because these two ones do not commute, but if you double it, it commutes. So the 9 observable that you create by doubling, all of them commutes, and you can create the subspace of maximally commuting observable generated by this guy, and you pick up a stabilizer state, and you get this state here. So because it's a stabilizer state, the product of the eigenvalue that you get from here and here should be +1, so they will replace the same eigenvalue. And you see this is what's implemented here in this circuit. You have this gate here that prepare this entangled 4-qubit state. And here we are measuring a context. So I don't remember exactly what this one is, but you see we are measuring. Okay, so here we are measuring directly. So there is Bob delegation qubit is here. So the Bob, okay, now I can say what we are measuring. So this is the observable y, this is observable x. So we are measuring yx here. And here we are measuring h, so we are measuring in the Hadamard basis, so this is xy. Okay? So we are measuring a 4-qubit observable on this entangled state. And so you can play the Mermin game with a circuit like this, and what we proved that we were able to, on a real quantum computer, win that game with the probability 0, with the frequency 0.93, which is bigger than 8/9. And this test of contextuality is even more exciting than the Rio-Negro inequality by itself, because here you do have a real protocol, like something you cannot do in the classical world, winning this game, that you can win with the quantum resources. Of course, here, because I'm not an experimentalist, far from being one, and I'm using some device that someone is controlling. So I cannot prove that they are spatially separated. You can criticize this very easily. But it shows that it's possible, as a proof of concept, that it's possible to provide some, to test some quantum protocols where you can do some things that you cannot do with classical limits. Okay. And do I have 1 minute more? Okay, so one natural extension of this, because yesterday I talked about these very nice geometries, the symplectic polar space, the doily, is can we create games based on these configurations? And can we create games with higher bound between the classical limit and the quantum limits? And first we created a game based on the doily, and we thought we had a better quantum gap between the classical and the quantum gap and the quantum limit. But actually Adam Cabello showed us we were wrong, because he was able to find a classical strategy based on different copy of the Mermin grid inside this doily. But we did find one variation of this game, which is called the point line game. So in this variation, instead of asking Alice to send back a triplet, we just ask Alice to send one value. And this value should be the same as the value corresponding to should satisfy the same constraint. So it's, in terms of geometry, Alice should give the result of one observable, and Bob should give the result of one line. And of course, the observable of which is on the line of Bob should match with the result given by Bob. So in this variation of the game, there is an advantage of playing with the full doily. The gap between classical and quantum is larger. Okay. Okay, so I stop here. Maybe just a few words about the reference on this second part of the talk. So this is a paper where Adam Cabello introduced this quantum contextuality inequality. This is a paper where I first implemented this test of quantum contextuality for the binary symplectic polar space. This is a paper with my former PhD, Henri de Boutré, and my colleague, Method Saniga, where we proved that so at that time in 2022, we didn't have this notion of contextuality, but we proved that a certain configuration inside W52 were contextual, and it was related to this split Cayley hexagon. So that's where we get this idea that this geometry has something to say about complexity. This is another paper we published recently where we did the full study of the hexagon, showing that they encapsulate this geometry of constraint. And this is a recent preprint with my former PhD Colm, where we propose some empirical demonstration of quantum contextuality by beating the classical bound of the Rio-Negro inequality and the Mermin game on a quantum computer. Okay, let's stop here.
We have time for a couple of short questions.
Yesterday you explained that calculating this degree of contextuality is very hard, and you use like heuristic algorithm to find bounds. I was wondering if with your quantum computers you can try to estimate this degree.
Yeah, that's a really good question. Actually, it's another project of Colm. We have another preprint on this. So Colm created a quantum algorithm, which basically is based on Groover algorithm. So where we test we put into superposition all contextual all classical assignments, and we use some variation of Groover algorithm to find the degree of contextuality.
Can you look at the spectrum for the second largest eigenvalue?
No. It's much simpler than that. It's basically okay. So that's what I explained also yesterday. The degree of contextuality is you have some assignment that correspond to the lines you want satisfied, and you look for a vector that satisfies as much as possible of constraint. Okay, and the degree is the failure, like how many equality you don't satisfy. And you can put in superposition all possible choice of X with a quantum computer, and you can translate the constraint of being on the same line with some Toffoli gate. Well, actually not Toffoli gate, but like control gates, which represent line of 3 points. So you implement all of the constraint, and you see how much you fail of being 0, 0, 0, or something like that. So yeah, so we have a project on this. It's still under review. So.
Other questions?
So in standard way, in standard pictures, we use always qubits, and we have Pauli gates or stabilizer gates with respect to qubits.
Qubits.
And yes, but this morning we learned about qdits, qtrits.
Mm-hmm.
Like for instance, you have those clock and shift operators of Weil-Heisenberg group. So is it thinkable to generalize this for qtrits, let's say?
Okay, so there is an analog of this picture for qtrits. Okay, this was I think Method Saniga has a paper on this, or if it doesn't have a paper, he already sent me the configuration. I can send you the corresponding configuration for two qtrits. It exists.
And last question.
Yeah, yes, you was waiting for.
Is there any analytic procedure to determine the space of maximum commutatively observables, given your number of states or your degree of contextuality?
So to find the maximal, so say it again, the maximal
the space of maximum commutatively observables that you mentioned there.
Well, okay. So the idea of moving or interpreting the n-qubit polygroup in terms of the symplectic polar space is that these objects have been studied mathematically quite a lot. So the subspace, so what you call maximally abelian subgroup in the generalized polygroup, they correspond to isotopic subspace of maximal dimension here. And we know how many of them, we know a lot of things about this. Okay, but finding the degree, it's our problem. There is no general procedure.
Okay, so let's thank our speaker again. Thank you. And now for the second session of Marek's course, again for 55 minutes.
Is it okay? Okay. Okay, so good afternoon. So I would like to start with some short recapitulation of what I have done of this construction I presented yesterday, namely that of momentum map. So at first sight it seems rather fancy, and I especially want to repeat a little bit about that because it will be the main tool which I will use in my analysis, further analysis, but I would like to stress that it is quite a nice idea, this momentum map, which has applications in many different places, okay, especially as I did it here at the very beginning in classical mechanics, when it could be used to investigate symmetries and conservation laws via some kind of Noether theorem, okay, and this is very universal tool. So in few words, once more, what was that? So we have some Lie group acting on a phase space. So the phase space in this case is a symplectic manifold. So you know already what is a symplectic manifold. This is a manifold with a closed to form, okay, and and the group acts on this manifold or on this our phase space via transformation which preserves the structures, these differential structures. So in classical mechanics, as I already mentioned, they are usually called canonical transformations, okay? So they do not change Poisson brackets, okay? Poisson brackets are determined by this symplectic form. So Okay, then all what we want to say, and then we can construct a map which goes from this manifold, our symplectic manifold, to the dual of the Lie algebra of the group. Okay, so Lie algebra of the group is the set of say matrices. Okay, and this is a linear space, and it has its dual. So which with elements of which can be also expressed as matrices, okay? So in a natural way, okay? I will tell something more maybe a bit about this. And the momentum map is actually what is the role of the momentum map is that for each element of the, for each element of the algebra, okay, we can define the map in this way, that this is our momentum map, which sends the points from M to the elements of the dual of the Lie algebra. So we can somehow apply this dual on our vector, on our element of the Lie algebra. So, and this is a function, this is a numerical function, and this function is the Hamilton function for this flow, which is induced by one parameter group generated by this Lie algebra element. Okay? And this is the core of the construction. Okay. So now we can do this, so we can perform this use this construction in different contexts. So for us, this is the once more the less transparency I showed you yesterday, a little bit improved, and I will tell you how, why, where. The symplectic structure, which is connected with the action on the group on its own Lie algebra. Okay, so you know that this is the natural action of the group on its Lie algebra, so-called adjoint action, which is defined here, which can be written in this differential format this way. Okay. So, then we define the coadjoint action. Okay. So this is the dual to this, dual by this pairing between dual space and our initial space. Okay. Okay. So this is the formula, and in all cases important for us, this mu is equivariant with the mu constructed previously is equivariant with respect to this adjoint action. And this is true in all cases which will be interesting for us, especially for semi-simple Lie algebra. Maybe it will be expedient to tell you what is, so to remind you what is a semi-simple Lie algebra, not because this is so important in the following, but this allows me also to introduce Cartan killing form, which will be used. So first, we can, for an A, which is the element of this Lie algebra, we can define an operator A, which acts on elements of the algebra by commutator. Okay. Okay. So this is so-called adjoint representation of the Lie algebra. Okay. And then, so this is some operator. Okay, acting on the Lie algebra elements, and now we can calculate. If we have such two elements, we can calculate trace of at A at B. This is also, see, if you choose some parameterization, so these are also matrices which are operators acting on our matrices, which are Lie algebra elements. And this is called killing Cartan form. And if this is non-degenerate, the algebra is semi-simple. Okay, this is not the definition. This is a theorem, but the definition of semi-simplicity is a little bit more involved in terms of algebraic properties of this. But this is not so important. So this is okay. And in our case, this K will be semi-simple. If you remember, this is either a direct product of unitary groups or special linear groups. Okay, so this is full field. Okay. What is interesting that on orbits of such an action, this adjoint action, this or co-adjoint action, there exists a natural symplectic structure. And this symplectic structure is described here. So it means that this adjoint orbits are really good phase spaces. Okay. Okay. So now, as I promised, we'll go to quantum mechanics finally from this, I would say, abstract algebraic or some classical mechanics formulations of this tool, okay, construction of this tool. Okay, so first, at the very beginning, what I said is that actually quantum mechanics lives, in a sense, not in the Hilbert space itself, but rather in the projective space of the Hilbert space. Okay, and this makes this geometrically interesting. Okay, this I contrasted with this algebraic. Okay, and this projective space happened to be a complex symplectic manifold. So it's which is a Kähler manifold. The Kähler manifold is a symplectic manifold, and which is complex, and this complex structure is compatible with this symplectic structure. What does it mean? So in complex space, you mean that if you take a tangent space at some point to this space, okay, so you can multiply the vectors by I, and they will stay in this tangent space. So this is really the complex structure. If it happens that this manifold is a symplectic manifold, and moreover this multiplication by I leaves this form invariant, so then this is scalar manifold. And this is very rich structure, so taking into account these two structures together, namely symplectic and complex. Okay. So how this is really, this symplectic structure looks like on symplectic manifold. So we have to calculate this on two vectors, okay, and this is exactly given by this form. Okay, so this is this complex. This is this symplectic structure which is here. It is easy to check that this unitary group of this special unitary group of this Hilbert space, of this our space, acts on this projective space by a symplectomorphism. So it does not change. So this is very easy to be seen from this formula. Okay, it does not change the form. Moreover, we can calculate the momentum map, and you see this is this one. Okay. Okay, and now let's attack our main problem. So we want to investigate entanglement. So we want to find the invariance, in a sense, of this action of this unitary group. Okay, so this is this local, so-called local unitary operations, so the operations which we believe do not change anything in entanglement because they are performed on individual subsystems, okay? Independently what happens in other subsystems. So this is simply a product of the unitary groups, each acting in one subsystem. Okay, so once again, this as it was shown here or said before. So this action of this unitary group is still is a symplectomorphism. Okay, it does not change the thing. And then you can easily see what is actually the image of this. These are simply the reduced density matrices of each subsystem. Okay, you have to shift it a little bit. Remember that because I insist that it goes into the Lie algebra or the dual of Lie algebra, which are traceless matrices in this case, and you know that reduced density matrices are positive, so you have to subtract actually 1/2 of identity to get it wrong. But in any case, this is the essence of this. So of this mapping. So now we want to use this fact to somehow investigate two things. So what are the entanglement properties, okay, upon investigating this image, okay, this set of density matrices, reduced density matrices, or maybe reconstruct. It is not possible in general, as you know, to reconstruct the initial state from the density matrix. Okay, so once more, the first two lines are repeat. This is what I have already said. So the setting. So we have this manifold, this group, and this is this momentum map. Okay. So look, now we can look at this whole picture in the following. So this is our manifold. This is this projective space M. Then we have some point, and so we want to investigate the class of points which have the same entanglement properties as this state X. Okay, so we are looking for the properties of the orbit of this group through this point. Okay, we can map this orbit to the dual of the Lie algebra via this momentum map. Okay, and to this orbit there corresponds an orbit in this dual space to the Lie algebra. Okay, actually this orbit is characterized by its intersection with something which is called Cartan subalgebra. So it means it means that via this unitary transformation, I can diagonalize actually the every matrix which is here. Okay, so I can put it to the diagonal form, and this diagonal form is an element of this Cartan subalgebra. Cartan subalgebra is maximal commutative subalgebra on the level of algebra. This is dual to algebra, but this can be identified algebra and dual of Lie algebra exactly by this Cartan-Weil form. Okay, so I can put it to diagonal form, and obviously there are many such forms because I can permute the eigenvalues. Okay, so I will fix it by ordering them. Okay, and this is so-called positive Weil chamber. Then I have a unique point here which characterizes this orbit in a sense, okay, via this projection. It definitely uniquely identifies this orbit, but somehow characterizes this this orbit upstairs. Okay. So if they are both, if these orbits are actually diffeomorphic, okay, so then all information which is here is included here. But here, what is the information I have here? There are spectra of the reduced density matrices, okay? So if they are diffeomorphic, so these are more or less the same things, okay? There is one-to-one correspondence between them. I can characterize my state X, or rather orbit through this, via spectra of reduced density matrices. Okay, so, but it doesn't happen too often. So first, this really happens if this orbit OX, so this is the case, so that both are diffeomorphic, for the orbits to the highest weight vector of the representation of K in H1. Here I remind you a little, so this small reminder, what is really the highest weight vector of the representation. So the algebra, or rather complexification of this algebra, so you can consider not only algebra, but the complex complexification is, so you can multiply by I an element and add to other element. So it can be always decomposed in such a direct sum. And this means that if you think about the, for example, unitary group or special unitary group, and then its and special unitary algebra, okay? So SUN, for example, so its complexification is special linear algebra, or special linear group on the level of group. So you can say that that it consists of some upper triangle matrices, diagonal matrices, and lower diagonal matrices. Okay, so these are this upper diagonal and lower diagonal are important because if they will commute them, so they will finally go to 0. And then the highest vector of the representation is the one which is the eigenvector of all these diagonal matrices, the Cartan subalgebra, and is annihilated by, say, n plus, okay? So, for example, if in the spin, everybody knows how to construct spin representation, say, for spin 1/2, okay? So this is exactly the vector jj for the spin equal to j, okay? So, so from this definition means that our orbit of this through the highest weight vector is there are coherent states in the per-ohm of sense. Okay, so and this is this is the case for separable states. So such a separable states lie on this say orbit of coherent states in this sense. Okay, so this was the highest representation. So it's clear that for the separable states you can really recover this. But in general, it is not so, okay? So there is a discrepancy with, or difference in dimensions of these two orbits. One orbit which is in the phase space and our space of states, and the space of this, and the space of the dual to Lie algebra. So you can define the difference between the two as kind of entanglement measure, okay? Discrete because these are the natural numbers, okay? So, and this is a kind of measure you can find from the momentum map. Okay. Okay. So this is once more this what I have already said, that you can define this Cartan killing form and forget that you are working in the dual of Lie algebra. This is really a Lie algebra itself. Okay. So this is what I said you, that each orbit is. And obviously there will be so that there will be it will be in one-to-one correspondence with the orbits in the state space with the orbits in the Lie algebra when this fiber -1 of is in this orbit, okay? So then this local unitary equivalence can be decided upon the spectra of reduced density matrices. So it means that if I have two states for which these two spectra are the same, so that means that they have the same amount of time. But this is not often, okay? Rather uncommon, okay? And to characterize the situation, we invoke so-called Brion theorem. Brion was a French mathematician who proved the following thing. So that K be a connected compactly group, as in our case. This is SUN, a product of SUNs, actually. And it acts on compact Kähler manifold. And this is our case, because this is exactly the complex projective space. And okay, and it acts by this symplectomorphism, okay? So it preserves omega. So that the following two things are equivalent. So G has open dense orbit in M and some Borel subgroup. You know what is Borel subgroup? A maximal connected solvable group has an open orbit in O. So we call it that action G on M is spherical in this case. And it is equivalent to this, that for every X, the fiber is contained in this chaotic. So this is the condition when we really can make. Okay, so we know that this is that for separated with states everything is okay, but how it comes that this is not okay? So there are some obstacles to this, to the spherical action. Okay. And the obstacle is the existence of so-called exceptional states. So first we can define the rank of a state. This means the minimal number of the states, the separable states which you have to use to produce the state. Okay, and this I will call it XR this. It is not written here explicitly. So this, what I defined in this line, is this XR. And this is not closed. So it means that there are states of rank R such that in the arbitrary neighborhood there are states of lower rank. So I would say the three most, straightforward example is the so-called W state, which has this form, okay? This is state of rank 3. And it can be obtained as a limit of a sequence of rank 2 states of such, from this GHZ state. And this is something which can be easily checked. That by this limiting procedure, you can obtain the rank 3 states from the sequence of rank 2 states. And if such states exist, or for such states, this action cannot be spherical, okay? Because the theorem states that the action is spherical, so it means that you can recover, okay, this from the spectra, in our language, if there are no exceptional states, okay? Okay, but for the exceptional state, you cannot do this. Okay, so it means that we need something more. In addition to the spectra of this reduced density matrices, we need something more. So to distinguish between different orbits, okay? In principle, you can, for this case of a compact group, you can distinguish the orbits by so-called invariant polynomials. What does it mean? So you have a state, okay, it has parameterized somehow, okay, so it has some coordinates, and you can construct a polynomial in this coordinates, okay? And and there are many of these polynomials. You have to have a set of these polynomials. If the set is large enough, then the values of these polynomials determine uniquely the orbit, okay? Obviously, this is completely independent of the parameterization, but just to make you, for you to see how it works. So this is so-called polynomial method. So we can differentiate between orbits via values of these invariant polynomials. This is not a very effective way, because first you have to find this polynomial. The second, many of them, and calculating them is okay. But nevertheless, you can ask, okay, so how many of these polynomials you have to add to your information contained in the spectra to uniquely determine this orbit, okay? So we were able to characterize in this way that let's consider such a map, which is simply this momentum map applied to the orbit times this positive chamber in the dual of the algebra, okay, positive oval chamber. So then there is a theorem by Kiron which says that this psi of M is a convex polytope. Okay, and it happens, so this is what we were able to determine, is how this number of additional parameters, of number of additional invariant polynomials, how large it is, to determine uniquely the orbit. And this is the result, that for L qubits, okay, so we have L of L subsystems, and in the interior of this polytope, this is equal to this one. Okay, so this is, you see that it grows exponentially with the number of qubits, which is unpleasant, but this is the story. Okay, but in generally it depends on the position in this polytope. This is true for the interior, and here is an example of a situation for 4 qubits. Okay, so for 4 qubits you have 4-dimensional. This polytope is in 4 dimensions. So these are 3-dimensional faces of this polynomial. Okay, they are characterized by some extremal points or vertices of this polynomial, which obviously correspond to some particular spectra of reduced density matrices. I didn't put it here explicitly because that's not so interesting. For example, this is for separable, this is for GAZ, and these are 3 different 3-dimensional spaces and faces, and you see that sometimes it is okay. So if it is no number, so it means that the number of this additional polynomial is 0. Here inside it's 12. Here is inside it's 2. But on the faces of these faces, it's 10, 8, 10, and so on. No, 10 on the faces and 8 on this 1-dimensional edge. Okay, so this is this. You know how poor is your information contained in the spectra. Okay, so this much for the local unitary equivalence. So it means that you investigated the properties invariant under this unitary transformation, local unitary information. As I told you yesterday, it's interesting also to consider this kind of stochastic local operations. It means that this operation which we perform on each subsystem is conditioned by the information, classical information I obtained from the other observers, okay? With a, I would say, potentially infinite number of exchange of information. And then you can show it was shown that then the group which corresponds to this is actually the special linear group. Okay, so in this case, direct product of such groups for say L subsystems. Okay, this is no longer a compact group. What does it mean? That you can still produce a ring of invariant polynomials which are finitely generated. Okay, so this is called Hilbert-Nagata theorem. But the orbits need not to be closed because this is not compact group. So invariant polynomials cannot in principle distinguish orbits with intersecting closures. Okay, because polynomials are continuous. Okay, so they do not intersect these orbits, but nevertheless the closure may intersect. Okay, and because they are continuing in such a way, in such cases, they cannot be used to distinguish orbits. Okay, because they should be the same on these two orbits which intersect with which closures of which intersect because of continuity, okay, of polynomial. So this is the other way of formulating is that the space, this quotient space M over G is non-Hausdorff. Okay. So we can construct something which is called generalized equivalent classes. So first we call two orbits. G is now in our group. It is not K because this is not compact now. So they are closure equivalent if if they closures non-equivalent if they are the intersection of closures is not equal to 0. Closure equivalent if this is not equal to 0. Sorry, it's how it is written. Okay, so the theorem says, I will obviously not prove this theorem, that if they really, if they do not intersect, okay, so they are not closure equivalent, then there is a G invariant polynomials which separates them, okay? So in this case, it's okay. I told you that if the closure intersect, you cannot distinguish it by a polynomial, but if they do not intersect, so there is a G invariant polynomial which differentiate between the two, okay? And moreover, there is enough such a G invariant, we can produce enough number of such G invariant polynomials to separate closed G orbits. Now there are the following things are true. That the closure equivalence class, okay, so this class of the orbits which are so connected, can contain only one closed orbit. Okay, if it contains more than one, then invariant polynomials would not be constant. Sure, because we can separate these closed orbits from the okay. And so we want to introduce a classification which is much more robust by organizing classes into a finite numbers of families, classes of these orbits. So this will be not so subtle, I would say, classification, and in the case of local unitary, but nevertheless. To this end, we use something which is usually called second convexity theorem, that this time the intersection of the momentum map of the closure of such a class of equivalence, okay, intersected with the positive chamber, Weil chamber of the Lie algebra is also a convex theorem. And there is a theorem which says that the collection of different polytopes is finite. And this is, so each polytope characterize some class of entanglement, okay? This is something which we call entanglement polytopes, okay? Okay. Wow. Okay, so now there are some subtlety. Namely, the set of points which is the closure equivalence class of orbits contains 0 as the unique closed orbit is called the null cone. And its complement in PhD, the set of semi-stable points. These are technical terms, which is not important. And the theorem says that each closed orbit contains only one K orbit, so this unitary part, so this part of this group of which our G is complexification, so this is this unitary. In this pre-image of this moment. So the stratification of this of the semi-stable points can be thus done by the points of this, okay? Because you have from this, you have to exclude this, which are you have identified this, which are put one to another by this unitary group. Okay, so this is the picture which you can say this is this our complex orbits. Okay, this is this intersection with our say the pre-image of this, and here there are some points. Okay, x2 and x1 of this intersection, and you take classes with respect to this unitary transformation. Okay, so if this the dimension of this is the dimension of the group, then the equivalence class through X consists of a single closed orbit, otherwise of an infinite number of them. So the topologically and geometrically it is quite complicated. What is nice is that this unitary orbit, this unique unitary orbit, can be found by such a gradient method, gradient flow of the square of the norm of the momentum mapping. Okay, and that such a flow by the gradient or minus gradient of that, so takes the point of takes a state to a critical point on the arbitrary orbit. So the orbits through x1 and x2 are equivalent if they are pushed to the same k orbit, which was clear from the previous one. Okay. Okay, so this is this complicated topological classification of this. So, okay, maybe I'll skip it. This is not so important at this moment. So the stratification of the space. In this case, so this say generalized equivalence classes or entanglement classes is done in the following. Then there is a finite number of different critical k orbits. That is finite number of entanglement polytopes, as I already said. And each determines one generalized equivalent class. Okay, and then an algorithm for finding. And this classes is defined as this set. This is usually a hard problem numerically. And then find this the set of all critical orbits in psi minus half. Psi was, as you remember, this mapping. Okay. And okay, but this can be done in the low dimensional cases, and we did it. Okay, so there are some results which I didn't put it because that. So up to 4, maybe 5 qubits. Okay, okay. I don't remember. I have to check what you have done. Okay, so these are the most important literature positions. So all this and much more is in these maps, in these papers. So these smart people are my PhD students at that time. Some of them are already professors now from this time. Adam Sawicki and Michał Szmaniec. Tomek Maciążek is actually a PhD student, and now he's graduated of Adam Sawicki. Thank you very much. Now questions.
Questions?
Frederick.
I have many, but
Okay.
just a couple of them. Yeah. First of all, the stabilizer state there must be isolated,
Yes.
so they must be classified by very specific type of polynomials, these
Yes.
entanglement polynomials. But suppose you have a state which is stabilized not by the whole bunch, but all but one, say, stabilizers. So you have all, not all, but all minus one monomials. In this case, is it possible to develop any classification starting with, this is called entanglement depth, probably you know. Is it possible to relate to the entanglement depth?
I cannot answer this straightforwardly, but I have to think about that. Okay.
Okay, but at least what can you say from the point of this polynomial view about stabilizer states? Can you say something specific? So they are
This is the
so
thing, because certainly I avoided, during all my work, I avoided invariant polynomials, okay, calculating invariant polynomials. I remember that Markus Grass gave once a nice algorithm for doing that, and then I dropped out from this moment.
Yes, Mike, you said a few slides before that the number of entanglement polytope is always finite.
Yes.
So
This polytopes, okay? Yes, so this is some yes.
okay.
So this is some theorem from symplectic geometry, or rather from this momentum map theorem. Okay.
And I also had another question, because I was a little bit confused by you before when you talk about orbit that intersect. And yes.
Okay, so these are two orbits, okay?
Yes.
Not closed, okay? This is not on compact group, okay? But it can happen that the closures intersect, okay? So let's assume that there is a polynomial which differentiates between them, okay? So it is not possible that such polynomial exists, because it should be equal on that, because it is continuous, so it should be continued with the same value to the closure.
But then I was thinking about the GSZ and W, for instance. They do intersect.
What?
The GSZ orbit and the W orbit, they do intersect, because one is contained in the other. And you can separate them in the 3-qubit case with
sure. But
this is not in
by this kind of but not by the polynomial.
well, the Cayley hyperdeterminant.
Pardon?
The Cayley hyperdeterminant. Well, we take the 2-qubit case.
Yes.
You have the EPR orbit, and the closure contains everything.
Closure by slug
By slug.
By slug.
Yeah, the closure by slug of the EPR
Yes.
contains a separable. But you can separate separable from EPR with a determinant. So that's why I was not.
No, you cannot. No, we have to discuss this.
Okay, okay, we can discuss this because yeah.
More questions?
This polytopes you showed like 2 slides, 3 slides before, they were done for 3 qubits. And
These were faces of this point.
yes, yes. But then, please remind me, so in practice, you can follow the same strategy to work with the case of, as you mentioned, 4 and 5 qubits, and have, do you know if somebody did, let's say, 3 Q-treats, or in this way is it too difficult?
Okay, in principle, it does not depend whether there are qubits or
in principle.
Q-treats, but it's so complicated for Q-treats that
And it's not
it
possible to
adopt-
plot polytopes because they are too
Yes.
many dimensional,
Yes.
and you don't see anything.
Yes.
Yeah.
And one last question.
First question is very quickly. Your momentum map is going from the Hilbert space to the dual of the algebra?
So in fact, in our case, it goes from the projective space to the dual of Lie algebra, okay? But obviously you can say that, okay, it goes from Hilbert space to Lie algebra if you take classes of equivalence, okay? So
Okay. And now, via your momentum map, you can pull back the symplectic form to the Hilbert space.
yes.
But also you can pull back your metric because you have a Kählerian.
Mhm.
But that metric, you can use it for something in order to describe or estimate the entanglement of actually it's not very
Not
important.
really, I don't know.
Okay. And also, you are like giving a very nice description of entanglement by these invariant manifolds. Have you ever think about some dynamics that is not going tangent because the unitary
Okay.
one is going tangent?
But something
once
which
it is
changes,
transversal,
which
yeah.
changes entanglement in a sense.
Yeah, yeah, yeah.
Okay, so you can, in a sense, you are prepared to study such dynamics, okay, on
Yeah.
this manifold. I've never did it.
Okay. But it can be like, maybe like the GKLS.
But yes, so
evolution.
this is a good idea.
Awesome.
You can do this.
Okay, thank you.
Let's thank our speaker again.